Yes, so let us start this session. Good evening, everyone. Am I audible? Please let me know in the chat box. Great. Yes. So let us start this session. And we have started with basically combinational circuits, and we have completed our combinational circuits, and uh, we have completed adders, subtractors, ripple carry adder, carry look ahead adder, and BCD adder, multiplexers, and multipliers we have completed, right? So this and all we have completed, and we are going to start with demultiplexers. And I hope you have also watched the session where we've also solved various problems related to multiplexers. Yes, we have still few more problems related to multiplexers and demultiplexers, encoders and decoders that we will solve in the upcoming sessions. And I will be somewhat irregular in the upcoming days since I'm busy with some other works. So I will be scheduling the sessions and I will let you know like before 3 hours or 4 hours itself so that you can plan your day, right? Yes. So coming to this particular demultiplexers, we have completed multiplexers in our previous sessions, and we have also tried to solve few problems related to multiplexers, right? Now coming to our demultiplexers. So let's start with demultiplexers. So this demultiplexer is opposite to our multiplexer, where in the case of my multiplexer, I was having uh, 2 power n inputs and one output, whereas in the case of my demultiplexer, I'm going to have one input and I'm going to have 2 power n outputs, right? And I'm going to have basically n select lines. So this is nothing but my demultiplexer, which I'm going to have, right? So coming to demultiplexer, if n is equal to 1, then you're going to have only one input and two outputs like this. So let's say this is y0 and this is y1 and one select line like this. Okay. So this is my input. So depending upon your input, you're going to, depending upon your select line, you're going to decide to which output your input should be connected. Let's say suppose if your select line, this is your select line and this is your input and this is your y0 and this is your y1. Okay. So if your select line is equal to 0, input is equal to 0, your y0 will be equal to 0 and y1 will also be equal to 0. If your select line is equal to 0, input is equal to 1, y0 will be equal to 1 and y1 will be equal to 0. So you can see if your select line is equal to 0, whatever the input is present, that will be present on your output. Okay. So if your select line is equal to 1, if your input is equal to 1, your y0 will be equal to 0 and y1 will be equal to 1. And if your select line is equal to 1 and input if it is equal to 0, then both the outputs will be equal to zeros. Okay. So this is how your demultiplexer is going to look like. So depending upon the select line, you're going to decide the input to which output it should be connected. Okay. Now coming to the equations of this demultiplexer, if I want to write down the equation of y0, it is nothing but select a complement into I0, and y1 it is select into I1. So these are the equations of my demultiplexer outputs. Okay. Yeah. Now, can anyone guess like what exactly, where exactly can we use this particular demultiplexer? Multiplexer, we have seen that when we are going to have multiple inputs, and if I want to select into a particular line, then we are going to use a multiplexer. And where can we use demultiplexer? Any application you can recall of? Where can we use a demultiplexer? Exactly. So if I'm going to have only single line and if I want to have, let's say, suppose if I'm going to have a single bus that should be connected to multiple buses like this. Okay. So that let's say this is bus number one, this is bus number two, and if this is bus number three, bus number four, and bus number five. So depending upon the select line, you're going to choose which particular bus you should have the connection. Okay. So this is where you can think of using a demultiplexer. Okay. Now, so coming to, I'm also going to have other kind of demux where I'm going to have, let's say, suppose if n is equal to 2, then I'm going to have 1 cross 2 power 2, which is nothing but 1 cross 4 demux, where I'm going to have select line is equal to 2. Okay. So I'm going to have two select lines over here. So this will be my demultiplexer, and where I'm going to have two select lines. This, let's say S1, and this is S0, and only one input and two outputs. Okay. So this is, sorry, four outputs. One, two, three, and four. Let's say this is Y0, this is Y1, Y2, and Y3. So the equation of Y0 will be S1 complement S0 complement into input, and this will be S1 complement S0 into input, and this will be S1 S0 complement into input, and this will be S1 S0 into input. Okay. So this is how your 1 cross 4 multiplexer is going to look like. And also you can refer to 1 cross 8 and 1 cross 16 and so on. Okay. Yes. Now, in the case of your demultiplexer, let's see one question, which is like, let's say, suppose you will be asked to implement a Boolean function. Let's say implement a Boolean function f of a, b, c, which is equal to sigma m 0, 2, 3, 4. Okay. Using demux. So this you need to implement using a demux. Okay. Now let us see how to implement this using a demux. So it's very simple. So since we have 3 bits, so 3 bits, and we are going to have total 8 minterms. Okay. So that means I'm going to take obviously 1 cross 8 demux. Okay. So I'm going to consider a 1 cross 8 demux, and select lines will be acting as A, B, and C. And input, I'm going to provide it as 1 itself. Okay, input will be provided as 1. And I'm going to have total 8 inputs like this: 1, 2, 3, 4, 5, 6, 7, 8, from Y0 to Y7. Okay. Now, what should I have? I should have 0, and I should have 2, and I should have 3, and 4 to be connected. That I'm going to give it an OR gate, and this will be my function f of EBC. That simple as it. Okay. So using this particular demultiplexer circuits, you can implement any Boolean function which is given. Like if you want, you can implement a full adder, or if you want, you can implement a half adder, you know, or you can implement any kind of Boolean function which is given using this particular kind of trick. Using a 1 cross 8 demux, you can implement this kind of minterms and all. Okay. So these are the kind of questions which you can encounter when you are attending your interviews. So you can look into this kind of questions also. Anyways, we are also going to look into this kind of questions and all. Okay. Yes. Now, before going to start with discussion of problems related to demultiplexer, let's try to start with the discussion of encoders, and we will come back, and once we will see the problems related to encoders, decoders, demultiplexers. Okay. So these problems collectively we will discuss. First, let's start with encoders discussion. Now, basically encoders are the circuits which are going to take 2 power n inputs, and it is going to provide n outputs. So let's say, suppose if my n is equal to 2, then I'm going to have basically 4 is to 2 encoder. Okay. So let's say, suppose if my n is equal to 3, I'm going to have a 8 is to 3 encoder. Okay. So let's first see the truth table of this encoder. Let's see a 4 is to 2 encoder. Then we will try to understand what is the behavior of this encoder with the help of this truth table itself. So coming to my 4 is to 2 encoder, let's say it is going to look like this. It's a 4 is to 2 encoder where I'm going to have 4 inputs: I0, I1, I2, and I3, and two outputs Y1 and Y0. This is my 4 is to 2 encoder which I'm going to have. Okay. Now, let's consider the truth table for this particular thing. So I'm going to have uh, I0, I1, I2, and I3. And this is Y1 and Y0. Okay. So this is my truth table of my 4 is to 2 encoder. Now, Using this truth table only, I'm going to tell you what is the behavior of this particular 4 is to 2 encoder. See, let's say suppose if I3 is equal to 1, the output corresponding to this I3 will be equal to 1. Or you can say this I3 is nothing but decimal equivalent of 3 and the binary equivalent of 3 is nothing but 1. That is what it is being producing, and remaining input should be equal to 0. Let's say what is the binary equivalent of 2? Binary equivalent of 2 is 1 0. That is what it is producing. And I3, I1, I0 should be equal to 0. Okay. So let's say if my I1 is equal to 1, then my binary equivalent of is equal to 0 1. This is a truth table. This is what my circuit should do. Okay. And let's say suppose if my I0 is equal to 1, then if remaining inputs are equal to 0, then my output should be equal to 0 0. Okay. So this is what my particular circuit should have. This is what the behavior that my circuit should be having. Okay. Let's say suppose if all the particular inputs are equal to zeros, then output is an invalid. I cannot have all the particular inputs of an encoder to be equal to 0. Then it's considered as an invalid input. Okay. And let's consider another cases also where I'm going to get invalid inputs I2 and I3 and Y1 and Y0. Now, let's say suppose if I3 is equal to 1, I2 is equal to 1 and remaining all are equal to 0, then also this is considered to be don't care. Okay. And when you are working with your encoder, uh, at a time, more than one input cannot be equal to one. Okay, so if you observe this page pattern, if you observe, only one input is one at a same single time. Okay, so more than one inputs cannot be one at the same time. If they are one, then you are going to consider your output to be unknown. That is what I'm basically framing in my truth table. Okay, and what else is possible? I cannot have double one double zero. It is also don't care, and double one zero one. It is also don't care, and triple one zero is also don't care, and what else I have, all ones is also don't care. Okay, so these are all the cases where I'm going to have don't cares. And what else I have, 001 0010 0011 and 1000 is present. Okay. And one more thing, let me write it down in the order. So where I3 is okay, here we are considering I0 as MSB and I3 as LSB. When I'm going to calculate the equations of Y1 and Y0, I'm going to get in these terms. Okay, so please be careful in this. I'm basically considering I0 as MSB in this particular truth table and I3 as LSB in this particular truth table. So when I'm going to calculate the equations of Y1 and Y0, I'm going to get in terms of I0 as MSB. Okay. So I've covered 0001, 0010, 0100, 0011, next 0100, and 0101 have we covered? Okay, we haven't covered 0101. Okay. So 0101 also we are going to consider it as don't care, and 0110 have we considered? We haven't considered 0100, 0110, and 0311 also we haven't seen. 0311 and 1000, 1001 have we considered? No. 1001 and 1010 have we considered? No. 1010. Here, all these cases, my output will be considered as don't cares only. And what else? 1101 we have covered. 1100, 1101 and 1110 4 ones. Yes. So all these cases we are going to get the don't case. And in only this particular cases we are going to get the proper. Okay. Now, so if I want to find out the min terms for my output, so y0 in terms of I need to have in terms of I0, I1, I2, I3. So what are the min terms I'm going to have is uh, this is one min term which is 1, and next this is 2. Next, this is 4. 1, 2, 4 and 8. 1, 2, sorry, only 1 and 2. If I'm going to calculate the equation of y1, I'm going to have only 1 and 2. So my minterms are 1 and 2. And what else we have? 1 and 2. That's it. We don't have any other minterms. And we have don't cares. So 0 is one of the don't care. 0 and what else we have? 0 and 3, 6, 8 plus 4, 12 plus 1, 13, 3, 6, 13, and 14 and 15. 3, 6, 13, 14, 15. And we have 5, 6, 6 is already covered, right? 7, 9, and 10. 5, 6, 7, 9, 10. 7, 9, 10 are my don't cares. Okay, so let me write it down properly. From 0, these are my don't cares. Plus don't care of 0, 3, 6, 13. These are all my don't cares. Now, can anyone form a key map and please let me know the equations of y0 which you're going to get? Please do it parallelly and let me know what is the equation of y0 you're going to get. It's a 4 variable key map which we are going to get and I need the equation of y0. Please solve it and let me know what is the equation of y0 you're going to get. Let me do it parallelly. And please remember the order which we have took. I0 is my MSB and I3 is my LSB. I0, I1 and I2 and I3. So 1 and 2 are my midterms and remaining all are my don't cares. 0, 3 and 6, 13, 15, 14 and 5 and 7 and 9 and 10 are my don't cares. So if I can group this, so what are the groups which we can form? We need to check for the octet and quad. So I can see a quad over here. Okay, is there any octet possible? 1, 2, 3, 4. Anyone getting any particular equations for this particular y0? Please solve this schema and let me know the equations. I0 into I1 complement. For y0, you're getting this up. I0 complement into I1 complement. Okay. Let me check whether we have took everything as correct or not. I think something we have took in this truth table only something wrong. Let me check it out. Y1 we have 1 and 2 and 4 and 8 are 0. 4 and 8 are 0 and next remaining all are don't cares. 3, 6, 13, 14, 15. 12 is also don't care now. Yeah, 12 is also don't care. 11 is also don't care. Now solve for it. Now what is that you're getting? 1, 2, 3, 4, 5, 6, 7, 8. If you form an octet, you're getting I3 common. You're getting different now. If you can solve this is an octet and take this 2 as an octet. So what is the common term in this is I3 plus I2. We are getting I3 plus I2 now for equation y0. Okay, one check it out. Everyone getting the same thing for y0? Y0 I am getting it as I3 plus I2. Once check it out whether I am correct or not. Yes. So generally what we remember is for the encoders we remember the equations as I3 plus I2, but how it is derived is this is the process which we are going to derive. We are going to write down all the possible combinations and we are going to derive the equations of y0 and y1. Okay. So once check it out, I'm getting I3 plus I2 using the schema method. Here in this both octets, I3 is common and in this 2, I2 is common. So I3 plus I2 is the common term. Okay. And the same thing you can do for y1. Okay. I have done it for y0, right? You can do it for y1. Okay. And you will get one more equation for y. Okay, and this is how we are going to have an encoder. Okay, so encode, how did I come up with the truth table? See, truth table is something which we are developing. Truth table is basically depicting the behavior of the particular circuit. What is our requirement? Our requirement is to have a circuit, a kind of encoder circuit, where the first condition is only one input should be one at the same time. No, both inputs or multiple inputs cannot be one at the same time. Then it should be considered as an invalid output. Okay, that is what we have depicted in the truth table. From this particular requirement, if we are solving this particular truth table, this is what the circuit is going to look like. So y0 is nothing but I3 plus I2. And anyone solved for y1? But it is preferred to do all once in single quad. You have a possibility of octet getting formed now. So why are you preferring quad? If we have a possibility of forming a octet, then why do we prefer a quad? Okay, Pranav? Okay, I got the other answer I1 plus I3. Great. So Y1, I'm getting it as I1 plus I3. So this is how your encoder circuit is going to look like I0, I1, I2, and I3. And your Y0 is nothing but I3 plus I2, I2 plus I3. You're going to give it to an OR gate, and Y1 is nothing but I1 plus I3. This is how your encoder circuit is going to look like. Okay. Yes. Is it clear, guys? Any doubts or any queries over here? Yeah. In the quad equation, what is that you are going to get? I0 bar into I1 bar. So in terms of your implementation, if you are implementing I0 bar into I1 bar, what is the gates you need? So you got the equation of y0 to be I0 bar into I1 bar, right? Two inverters and one AND gate. But if I want to implement I3 plus I2, what is that I need to have? How many gates should I have? Only one OR gate now. So which do you prefer? Two inverters plus one AND gate, or do you prefer one OR gate? Exactly. Okay. Yes. So in this particular circuit, if we have observed in the case of my encoder, only at a time one input should be equal to one. And if more than one inputs are equal to one, I'm going to enter, it's an invalid state, right? Now, for overcoming that, we are going to have other kind of circuit which is known as priority encoder. Okay. So in the case of my priority encoder, I am going to give the priority to the inputs. Okay. For example, let's say I3 has the highest priority compared to I2, compared to I1, compared to I0. This is my priority order I'm going to have. Okay. And let's keep the truth table. Now, here I'm considering I3 as MSB and I0 as LSB. Okay. 0, 0, 0, 1. My output should be equal to 0, 0. Okay. And 0, 0, 1, 0. My output should be equal to 0, 1. And 0, 1, 0, 0. My output should be equal to 1, 0. And 1, all zeros, my output should be equal to 1, 1. This is my encoder. Now, let's say in the encoder, if I'm going to have double 1, previously I was considering unknown. Now, this is considered as 0, 1 only. You can see there is no effect of I0 whenever your I1 is equal to 1, because I1 has the highest priority compared to I0. I0 has no effect when your I1 is equal to 1. I0 can be 0 or I0 can be equal to 1. So that's the reason I'm going to consider this as a don't care. So I0 can be any bit. If your I1 is equal to 1, you are going to consider your output as 0, 1. Similarly, if I'm going to have I3, I2, I1 and I0, and this is Y1 and Y0, and if I'm going to consider, where is this? 0, 1, 1, 0, then my output should be equal to 1, 0. You can see over here, there is no dependency upon I1. If your I2 is equal to 1, you're not going to care upon I1. I1 may be any bit, it might be 1 or it might be 0, you're going to get 1, 0. And there is no chance of I0, there is no effect of I0 also. Okay, so that's the reason I'm writing it as don't care. Don't care in the sense it might be 0 or it might be 1. It might be 0 or it might be 1 whenever your I2 is equal to 1. Whenever your I2 is equal to 1, circuit is going to provide the output corresponding to I2. That is nothing but 1, 0. And whenever your I3 is equal to 1, you're not going to care upon the remaining bits and your output will be equal to 1, 1. Okay. This might be 0 or this might be 1. This might be 0 or this might be 1. 0 or 1. You're going to get the output corresponding to I3. Okay. So that is nothing but my priority encoder. Okay. So priority encoder, this is not the fixed priority. It's you can decide what can be the priority. It's up to you. Okay. So it's not like you should give the priority to I3 and then I2, I1. It's your wish. You can decide I3 has the highest priority compared to, you can also have like this also. I3 has the highest priority compared to I1, compared to I2, compared to I0. This also you can have. Nothing wrong in it. Okay. Now, so this is nothing but my priority encoder. Your simple task is to come up with a circuit. So how to come up with a circuit or the logic diagram or the Boolean expression? This is the steps you need to follow. You need to follow the same steps and you need to come up with the equations for y1 and y0 so that we can have the discussion. Okay, I will explain you how to, elaborate uh, whenever you have x in your input side, how to come up with the equations. I will explain it. Okay. Once give it a try and we will discuss. Yes. So that's about this particular session. If you have any doubts or any other queries you wanted to discuss, you can stay and discuss with me, or else we can wrap up the session. Okay. Thank you.